let's see. Monday, we had just finished adding hydroboration oxidation to our table. All right, so I think I'm going to official count on how many reactions we're going to have for the exam. And that number is going to be 9. So 9 reactions. I thought it was going to be as high as 12, but we're not going to get that far. And ultimately, some of them are just derivatives of things we've already learned. So I think we're going to cut it at 9. We might get through all those today, leaving us Friday to, just look at some examples, some nuances of this stuff, maybe take some questions, and ready to go in on Monday. All right, so our song today is Superstar, the Carpenters cover by Sonic Youth. And so I don't know, it just came on honestly while I was in the shower, and I like the song, so that's our theme song today. But I just want you to know, I think you're all superstars in my heart at organic chemistry. So let's see. This was Sadie on campus last week. I had told her to sit, and she did, and so she's pretty good at following commands these days. Yeah. Oh, and so funny thing. All right, so I don't have a lot of funny things today, unfortunately. It's part of the job, right? So I told my wife I wouldn't tell anyone this, so I'm going to. Oh boy. And so my wife is a vivid dreamer. She wakes up every morning and it's like 5 minutes of just hearing what she dreamt about. And so this time, and here's why I think this is on her mind. So who had Professor Meldrum last semester? He and his wife are having their second child today. So, today, literally. At the hospital? At the hospital. I don't know what they're naming it. I'm not privy to that information. They didn't tell me. So, anyway, I think my wife kind of had children on her mind.
Get another dog.
Yeah, second dog. Anyway, she wakes up and she's like, I dreamt that we had a baby. And I was like, all right, well, fine. And she was like, and we named it Edward Cullen. and I was like, no. And so I thought two things. I was like, number one, why did we give it a different last name? and then secondly, I got a little panic because I was like, oh, so you're in Twilight now. And she was like, look, it was just like the normal. I was in 8th grade. It was the normal thing people did, and I never did it again. And so we're good, my wife and I, this morning. So anyway, our potential child, Edward Cullen. And also, she said it turned into a puppy later. So. She subscribes to my YouTube channel, by the way, so she'll probably hear this. She always listens to the first couple of minutes of class. All right, so let's get cracking on this. All right, so we're just gonna jump into reaction. Is it number 7? Yes, number 7. All right, so my numbering is 1 off. All right, so number 7. This is a good one. All right, this was really exciting. So, what we're going to end up with, or at least what we'll start with, we'll go with our trusty cyclopentene, or 1-methylcyclopentene. So we're going to react. This is going to be another 2-stepper, and so that means we're going to have an important step that we'll know the mechanism for, and then we're going to have a workup step, because the stable intermediate in the middle is not something we're interested in. Especially because osmium, I think, is fairly toxic, and so we want to get rid of the osmium off of our molecule. All right, so let's see. We're going to treat this thing with osmium tetroxide. And so potentially down the road somewhere, you could also see this reaction done with KMNO4, but we're just going to keep it to osmium tetroxide mechanistically. It ultimately goes through a very similar mechanism. And so then once we've hit our molecule with osmium tetroxide, we're just going to throw some water in there. And so that's our workup. All we got to do is treat it with water, and that works it up for us into what we want. So what kind of molecule do we get out of this thing? All right, so of course our ring stays the same. We're going to have our methyl group. All right, and so first off, this is a concerted mechanism, which means is it going to be syn or anti? It's going to be syn. So whatever we're adding to this thing, we're going to add to the same side. And so ultimately, what we'll find that we're adding is to the front side on the tertiary carbon, we'll add an OH. We've seen that before. On the secondary carbon, on the top side, we'll also add an OH. Wow, we added 2 OHs. That would be referred to as what kind of molecule? A diol, right? All right, so there's 2 of them, and so we call molecules with 2 alcohols a diol. So ultimately, we're able to convert our alkene to a diol using osmium tetroxide. And of course, what else is a possibility? That molecule plus the enantiomer, right? Because what we could also do is have our osmium tetroxide add in from the back, and so in that case, the methyl gets pushed forward. And so ultimately, we could also, oh, that's not right. There we go. All right, so it's going to be a syn addition, and so we'd have that diol as well. So two possible products from this reaction. All right, so let's look at the mechanism. This one's kind of a nifty one. So let's see, mechanistically, let's start with a cyclohexene. And so what does osmium tetroxide look like? Well, it's osmium, and basically it's just going to have double bonds to a bunch of oxygens. So we'll have one here, and one here, and one here. All right, so there's osmium tetroxide. Ultimately, that thing's making 8 bonds, but it's a metal. It can make 8 bonds if it wants to. Metals do funky things. Carbons don't. All right, so let's see. Where do you think we're going to start our arrow? On the alkene, right? Every time we do this, we start our arrow on the alkene. So that's what we're doing. So where we're going to draw our arrow to is actually going to be the oxygen. All right, so let's go ahead and fill in our lone pairs so we can see specifically what's happening. All right, so we're going to go ahead and attach it to our oxygen. Now, if we're going to form a new bond between a carbon and an oxygen, well, how many bonds would that oxygen be making? Or at least the better question would be, would we be violating the octet rule? Yeah, we would be violating the octet. Yeah.
Why didn't we switch to a cyclohexane?
Just for the heck of it. It's going to be the same mechanism with any ion. I just am showing a different molecule. And so I certainly could have different molecules on the exam that I would expect you to be able to work through. Okay, so we've just got a random cyclohexane, and so also it's just for simplicity. There's not a lot of stuff there, and so it'll help us narrow down the mechanism. Okay, so we're going to violate the octet rule if we form this new bond between a carbon and an oxygen. And so what we've got to do is we're going to have to break the pi bond, right? So the electrons involved in that pi bond between osmium and oxygen, they're going to rush back to the osmium. But now we've got a charge built up on osmium, and so at the same time, what we can do is we can take another pi bond and draw it back to the other carbon. All right, so we've got 3 arrows going on, and most of these are, I think in all of these concerted mechanisms, we've seen 3 arrows, and so it's the same thing. All right, so what do we end up seeing? Since this is a concerted mechanism, we've already said it's going to be a syn addition. This is going to be happening on the same face of our double bond, and so we'll just assume that it's attacking from the front side. If it's attacking from the front side, what we end up with is going to be a structure. We're going to have a 5-membered ring.
Why a 5-membered ring?
We'll see why it's a 5-membered ring. We still have our 6-membered ring, but we're going to form a new 5-membered ring. All right, and so that new 5-membered ring is that guy right there. All right, so we've still got our 2 pi bonds over here. We've also added a lone pair to the osmium. Okay, so we formed this new 5-membered ring that's now attached to our initial 6-membered ring. And so this is our stable intermediate. All right. Stable intermediate. And so we don't ultimately, any of the drugs we've looked at, they've never had osmium stuff connected to them. And so ultimately we want to kick that off. And we know we're going to end up with a product that are diols. And so all we're going to do is then add H2O. And so we don't worry about the mechanism behind the workup step. We just want to know that what we're going to end up with will then be an OH group on top and an OH group on the bottom. And we're showing those syn because ultimately our first step, our addition of our osmium tetroxide to our double bond, has to add to the same face as I've shown. All right, so not really too bad once you get the hang of this, and I would definitely practice kind of drawing through that a little bit just so you're comfortable with what's going on there. All right.
Is there an enantiomer?
What's that?
Is there an enantiomer?
In this case, there would not be an enantiomer because the other possibility is we would add from the back face. And so what would the relationship between these two be?
It's the same thing.
Those are the same molecule, right? Just flipped over. Yeah.
So could you explain again how you get this stable enantiomer? I'm kind of confused by that 3-step.
So this is, what it is basically we're going to have, the way this must work out charge-wise is we must have a little bit of a partial positive buildup there because we're getting attacked by some electrons. So ultimately it's one of these mechanisms that you just kind of have to memorize. It's, and this is the first time I think you've seen something a little more complex like this, but it's just how it goes.
I'm just curious, are most workups, do they end up attaching the hydrogen at the end?
Workups, it's dependent on the nature of the workup. Sometimes your workups will be water, sometimes you'll have an acidic workup, sometimes you'll have a basic workup, sometimes you can have an oxidative workup or a reductive workup. It just depends on the nature of the workup. Lauren?
I was just wondering what the name of this mechanism was.
The name of it? I don't know. What I would call it is the mechanism of osmium tetroxide with an alkene. Yeah, I don't know that it has a specific name. Yeah.
So it's a workup, just the stuff that we don't understand the mechanism of?
Yeah, we're just not too worried about it. In a lot of cases, we do understand it, but it's clearly straightforward and simple, and so we don't even care too much about it. In some cases, we actually, it is a lot more complicated. And so we're going to see a reaction here later in class where I'm going to skip a big chunk of the mechanism because it's actually really complicated. Yeah. Rhea.
So that third arrow that you drew, you're drawing it directly from the pi bond to the carbon itself, right?
Yep.
Okay.
And so basically, these electrons, they stay connected to this oxygen, but they're leaving the osmium. So this end of the bond is basically going from the osmium to the carbon. Yeah. Yes. Yeah, you.
So what happened to the osmium on the...
So that's a good question. So that osmium is, I'm not sure what ultimately the product would look like, but I will say it's not going to become one of these again. So we're going to have as many pi bonds as we have, we're going to have just as many of these because each equivalent of osmium tetroxide will react with one equivalent of the pi bond.
We just leave it out?
Yeah, you can just leave it out. We're not too concerned with it. We're mainly just concerned about our organic product. Yeah, Sarah?
Why would bonding the pi bond to the oxygen break the octet rule? Like, couldn't you just have the oxygen have a formal charge of +1?
Because it's a second row element. It just can't break the octet rule. We don't have enough orbitals there to have 5 areas of electrons. That's where the octet rule comes from in the first place. Yeah, in our second row elements, we know that we just have one s orbital and then the 3p orbitals. And so all we have room for is 8 electrons. Yeah, Josh?
Is it reasonable to think that the pi bonds in the 6-figure ring and the oxygen effectively become the wedges and or dashes in the stable intermediate?
Yeah, so ultimately what's becoming those wedges is going to be this arrow and this arrow, right? So 2 of those arrows are basically just showing new connectivity. And then the third arrow is just showing this necessary elimination of this bond to avoid breaking the octet rule. Yeah. Other question? Yeah.
Can osmium break that octet rule because it has that lone pair?
Yeah, osmium can break the octet rule because not only is it not a row 2 element, it's way down here. There's so many orbitals in there, it's going to do ridiculous.
All right.
Yeah, lots of orbitals in osmium. We good?
Yes.
Okay. All right, so let's go ahead and add that to our table. All right, so this is reaction, we said 7. So really, our nucleophile, or what results is our nucleophile electrophile addition. It's the same thing. We have an OH on one side, and we had an OH on the other. So the way way that we're going to go about this, anytime that I'm going to test you on it, it's going to be osmium tetroxide followed by a water workup. Regioselectivity, since ultimately this thing and this thing are the same, do we really show any regioselectivity? No, we can't tell, right? And so we say that there's no regioselectivity going on here. Stereoselectivity, definitely sin. And so this is going through again a concerted mechanism. Okay, so that is our addition of osmium tetroxide. So let's see. So we've got two more reactions we're going to ultimately end up learning, but I kind of wanted to take a little bit of a timeout and just kind of solve some problems and just play around with some reactions for a few minutes. So that's what we're going to do. We'll take a little time out and filling in our table. So what you can see, what you can be asked is a question such as this. So let's ask ourselves, there's going to be a question box, and then you can see a reaction. And so I'll even give you the reaction. I'll leave these out right now. I'm just going to give away the answer. All right, so what we're going to end up with is a product that looks like this. All right, so we're going to have a methyl back, hydrogen forward, and over here we'll have methyl back and hydrogen forward. Okay, and so what you could be asked is, you need to not give me the product of this reaction. What starting material could we be expected to give us this product? And so what I want to do as we go is kind of pay attention to our stereochemistry. So if we call that 1, 2, 3, and 4, is that going to be R or S on the left carbon? So if we put our thumb towards our hydrogen coming towards us, can we curl 1, 2, 3? Yeah, we can with our left hand, so that's going to be an S stereocenter. And so then the one on the right, we've got 1, 2, 3, 4. And so what would that be? So yeah, it looks like S still, right? Because if we put our thumb out on the wedge, we can curl 1, 2, 3 like that. So ultimately what we've got is the SS stereoisomer here. And so first, let's think about what we've learned. All right, so we've got 7 reactions in the toolbox now. We know how to do 7 transformations. And so have we learned a reaction where ultimately we add 2 alcohols to something? Yeah, I mean, we just did it, right? So we'll go ahead and say, yeah, we know how to do that. So we know that that's going to be an osmium tetroxide reaction followed with a water workup. And so specifically, we know that the stereochemistry of this reaction has to be what? Yeah, it has to be sin. It's just the nature of the mechanism, right? So we know what mechanism it goes through, and so it has to be a sin addition. Now, when we look at this product, all right, if it's a sin addition, would we end up with the alcohol on opposite sides? No, right? What we're showing right now are those alcohols anti to each other. And so what we've got to do is we've got to basically orient our final product in such a way that now the things that we're adding, the OH groups, are sin. And so we know it has to be sin because that's the sort of mechanism it goes through. So how could we align these things to be sin, the 2 OH groups? Yeah, we're going to have to rotate one of those carbons 180 degrees, right? All right, so let's do this 2 ways. Let's do it as I've shown, and then let's do it through a Newman projection, just so we can maybe clarify. All right, so we're going to draw a Newman projection that's looking down the CC bond from the left side. And so when doing so, we'll draw our Newman. So we've got a hydroxyl group on the top side, methyl to the bottom left, and a hydrogen to the bottom right. So then we've got our OH on the back carbon, hydrogen to the top right, and methyl to the top left, right? So that's the picture that we're looking at, basically. These 2 things are the same exact molecule and the same exact conformation. All right, so let's undergo a bond rotation. And so what I'm going to do is rotate the right carbon 180 degrees. And so if we rotate the right carbon 180 degrees, we're going to keep the left carbon still. And so we'll have the same exact picture on the left side. right side has changed. So now our OH group, is it still in the plane? Yeah, it's still in the plane, right? So in this picture, it's in the plane going down. It's just if we rotate it, it's going to be in the plane, but now it's going to be pointed up. And so there's our OH group, and so we'll have a wedge and a dash still. And so what's going to be on the wedge, on the bottom right there? Yeah, it should be the methyl group, right? The methyl, everything basically on the right side is going to flip 180 degrees. And so if the methyl is going back into the board, well, 180 degrees to that, just like this pin. If the top of it's going back into the board, well, the bottom of it, which is 180 degrees, is coming forward. And so we end up with our methyl on a wedge. And so that means our hydrogen must be right there. What are the have we undergone any stereochemistry change here? No, it's still SS, right? Because we can undergo bond rotation, and that's just something that happens in an sp3 bond. That's going to continually happen, but we still haven't changed our stereo centers. And if we worked out our stereochemistry, we would see that we've still got S there, and we've still got S there. So that hasn't changed whatsoever. All right, so let's draw our Newman projection. Is this going to be a staggered or eclipsed conformation?
Eclipsed.
It's going to be eclipsed, and so we've got our hydroxyl groups eclipsed now. Hydrogen, methyl to the bottom right. On the front carbon to the left, we've got methyl. And on the back, we've got a hydrogen. Okay, everybody happy with that? All right, so basically we're looking at that picture from two different ways. And so now, do we have our alcohols aligned such that they're syn to each other?
Yes.
Yeah, they're on the same side, is there?
But the methyls and the hydrogen are no longer syn. Is that okay?
We don't care about that because we're not adding a methyl or a hydrogen, right? We're just adding the hydroxyl groups. And so it's the things that we know we're adding to ultimately what will be the double bond.
So only the things we have to add have to be syn.
Yeah, we're only concerned about the things we're adding to this double bond. Yeah.
How do you know they're eclipsed?
So we know that we learned basically two conformations, right? So they're staggered when we have 60-degree angles between our substituents. They're eclipsed basically when they're just overlapping. And so if we were looking down this molecule right here, let's see, we'd be looking from, I do this kind of poorly, we'd be looking from that kind of perspective. And so we know that the hydroxyl group here would be straight up. And so on the back carbon, it would also be straight up, right? And so we theoretically wouldn't be able to see the back hydroxyl group because it would be eclipsed by the front hydroxyl group, just like a solar eclipse, right? All right. So let's see. So what we've done is we've essentially rotated such that now our hydroxyl groups are syn to each other, so they are on the same side. And so what we want to do is then we see, well, what groups are together? All right, so we know that we've got a hydrogen and a methyl together on the bottom left. And we've got, let's see, let's go to gray. A methyl and a hydrogen together on the bottom right. And so what that means is that when we ultimately draw our product, we're going to draw it such that we have a front carbon and a back carbon. So the two things together in that blue box are going to be on the same side of our double bond. And so what we would show is on that front carbon, we've got a methyl, so we'll show a methyl there. What needs to be in this position there? That needs to be a hydrogen, right? Because those two are together here. And if you kind of imagine what you're looking at, if you pretended that we plucked off those hydroxyl groups, we could kind of imagine an alkene, right, that we're looking down the bond. And so on the left side, on one side, we would have our H and our methyl together. And on the right side, we would have our H and our methyl together. And so then on the bottom, we've got a hydrogen and then a methyl on that side. And so ultimately what we're kind of doing is we're changing our perspective. If we kind of look down that bond right there, what we would see is we would see something sort of along the lines of, and so now we're looking at an sp2 hybridized atom, so we're not going to have the trigonal planar, not the trigonal planar, but the tetrahedral angles. What we really would have is something that looks kind of like, let's see, we'll keep the methyl there, hydrogen there, and then on the other side we would have hydrogen there, and methyl there. And so can you see how basically this picture is pretty much this picture? Yeah, and so what we've done is we've basically plucked off these hydroxyl groups. These two groups have just spread back out because we've changed the hybridization, so these are going to come upwards just a little bit to give us this picture, and now ultimately what we've got is this alkene that we're looking down this way, and so we can see that the methyl and the hydrogen are on the same side, and then of course on the right side we've got a hydrogen and then a methyl in the back. Alright, so this takes a little bit of practice, but the ultimate point of this exercise is the fact that what we're learning is that the stereochemistry of the product depends on the stereochemistry of the double bond. Alright, so we can see up top, we were showing a product that was the SS stereoisomer. And so can we assign a label to this molecule right here? Sure, we can give it an EZ label. And so what would this be? Yeah, so this is, now we've got an E double bond. And so we can see that our E double bond is going to lead to an SS. So let's see what would happen if we tried it with the Z double bond. Let's see if this is, see if I'm telling you the truth or if I'm just biased. All right, so let's try it with our Z product. And so with the Z product, we're going to have our methyls on the same side. So in that case, let's draw something. We'll put our methyls on a wedge going back. And so I want to draw this with depth so that we can see a little more clearly what's going on. So our hydrogens will be on the same side. All right, so does everyone agree that this is now the Z double bond? Yeah, all right, so we've got the Z double bond here. And so let's hit this thing with osmium tetroxide. So now what do we know about the stereochemistry of an osmium tetroxide reaction? Got to be syn. And so what we end up with is a product. We're going to have our carbon and our carbon. And so we're going to show our diol on the left side and our diol on the right side as syn to each other. And so in doing so, when we add in our diols from the top face, what's going to happen is these groups are going to get pushed down, right? And so if the hydrogen's on a wedge, will it still be on a wedge over here? Yeah, absolutely. They're just getting shoved down a little bit. So what we end up with is a methyl here, a hydrogen there. On the other side, the same thing happens. So basically, the osmium's going to push our groups down so that we have a structure that looks like that. So now let's figure out the stereochemistry. So we've got group 1, 2, 3, and 4. And so what's the stereocenter on this left carbon? Looks like S to me, right? So if we've got our thumb on a wedge, we can curl 1, 2, 3. So that's going to be S. And then on the right side, let's see what we've got. We should have 1, 2, 3, 4. And so yeah, now what we see is we would curl, we'd put our thumb on a wedge. With my right hand, can I curl 1, 2, 3? Yeah, absolutely. So now we can see that we end up with the SR stereoisomer. And so what we're seeing is that with the E double bond, what we would end up with is the SS stereoisomer. With the Z double bond, we would end up with the SR stereoisomer. And so what we get are different stereoisomers based off of our beginning product. All right, so we're leaving out a product. Yeah, Gabby, you got a question?
Yeah. Why did you put the methyls on dashes? Is that arbitrary?
It's because they were on dashes in our Z here, in our Z alkene. We could have also put them both on wedges, but what we'd end up with is basically the same product. All right, so what we know is that we've added our hydroxyl groups from the top face, but it's a planar double bond. So could we also add our OHs from the bottom face? Yeah, absolutely. And so in that case, what we would get all right, so on the left side, we have our methyl on a wedge, and so it will stay on a wedge. It's going to be pushed up now. Our hydrogen is, I misspoke. So the methyl is on a dash here. It will stay on a dash, and so the hydrogen is on a wedge, and our starting material is still on a wedge. The other side, we'll see the same thing. So our methyl is is there. Our hydrogen is here. And so what we would find if we worked out the stereochemistry knowing that this is 1, 2, 3, 4, we would see that this is going to be, let's see. So this is make sure I did this right. All right, let's go ahead and prioritize over here while we're at it. 1, 2,
Yeah, see, if you roll,
Three,
if you
keep
roll- Yeah, if you rolled your wrist enough, you can get the 1, 2, 3, like you don't pop your wrist out. Yeah, that's right.
all right, so this one is definitely S.
Same way.
So this one is definitely R. Yeah, okay. It should make you feel a little better that sometimes it takes me a minute too, right, to look at these things and figure it out. Okay, and so what's the relationship between these two molecules?
Enantiomer.
Are they enantiomers?
Guys, dude?
Do you see any symmetry in this molecule?
Oh, you learned amazing.
What if we say that there's a plane of symmetry that's pretty much the plane of the paper?
Yeah.
Would that be true? All right, let's prove it. So what we've got is we've got a molecule. Actually, maybe the easiest way to show this is what if you took one of these structures? All right, so here's my structure, and I do this to it. I just flip it over 180 degrees. Are those different molecules?
Yeah.
They are the same molecule, right? So what do we have in this case? We have a molecule with chiral centers, but it's ultimately achiral. So what we have here is an example of a mesocompound. So ultimately, if we had our Z double bond and we treated it with osmium tetroxide, we would end up with one product because top attack as well as bottom attack would give you the same product because of the symmetry. Okay. Let's do another one. That was fun. All right, so in this case, let's say we end up a lot of talking. Any questions? Yeah.
So for a question like that,
Yeah.
would you ask something more specific, like what is the starting material, or you know, is it SR, like something one piece, or is it just regurgitated?
Yeah, so what I could do is I could show you some product and basically ask you what would the starting material be. Would it have to be E or would it have to be C? One of those, in a lot of cases, will give you that specific product. Yeah.
So like for this, we said that a Z results in an SR or RS product, or an SR or RS, and an E results in an SS or RR. And like here, we got a meso from the Z, but can that be generalized to, or is it different for everyone?
Yeah, and so you definitely do not learn this and think that all E double bonds are going to give you SS, all right? It's going to be dependent on the molecule in question.
So it's like totally independent.
Yeah, you're going to have to figure out the stereochemistry in each case. So what we see here is that we call this E, we get the SS, and so we did that by figuring out the stereochemistry. Yeah. Rick?
I'm a little confused why on the right one we aren't switching the methyl like to be on a dash and the H to be on a, the other way around. The methyl to be on a wedge. And then, because if you're are you flipping, rotating each bond, or are you flipping the whole, like, molecule?
You mean the relationship between the two?
Or like why we aren't switching the dash and the wedge when you're
He didn't rotate it, he just added
You
it
just
up.
added it.
All right, so if I have my hand like this, you see how my pinky's coming towards you? If I flip this over, is my pinky still coming towards you? And so it was on a wedge here, it's also going to be on a wedge here. Yeah. Okay. So in this next case, let's say we've got a product. Looks like this. All right, so have we learned some way that we can add a couple of chlorines to a molecule? Sure, we hit an alkene with chlorine gas, so Cl2, and so what we find is we add the chlorines to both sides of the alkene. Now, speaking about the stereochemistry of this reaction, is it syn or anti? goes through a halonium-type mechanism, and so anything that goes through a halonium-type mechanism gives you what kind of stereochem? Definitely anti. All right, so we're going to go through an anti-type mechanism. And so our chlorines, are they aligned anti to each other? No, and so what we're going to have to do is we'll have to undergo a bond rotation to make them anti, so keep the left side the same. And so we'll flip this chlorine down such that now it is anti. And so in doing so, what's going to be on a wedge up top? Yeah, it should be the hydrogen, right? Because we're also changing the hydrogen to 180 degrees, and so it was on a dash on the bottom, so now it should be a wedge on the top, and so vice versa. We'll have a methyl that's now going back into the board like that. Okay, so are we anti? Yeah, so what we can do is we want to think about what's on the same side of this molecule. So we've got a methyl and a hydrogen coming on the wedges, right? So they're on one side of ultimately what will be the double bond. So let's say we're looking down. We'll go ahead, let me draw this out so everyone can see it more clearly. So we'll draw a Newman of this. All right, so we've got our chlorine, and those are anti to each other. We've got a methyl here, hydrogen, methyl. Okay, and so essentially what we're doing is we're looking at the two things on the right side, or on the same side of this Newman projection. So is everyone happy with seeing how this methyl and hydrogen that I've circled are also this methyl and this hydrogen?
Yes.
Yeah, and so what we're going to end up with for a starting material, we would have those two things on the same side. So let's keep our orientation the same. We'll call it our methyl in front. And then connected to that, we'll have our hydrogen. So vice versa on the other side, we've got that hydrogen and that methyl. So that's hydrogen, methyl, and so it's, let's see, we want hydrogen here, methyl on the back. And so looking at this product, I could ask you, would it be the E or the Z starting material that could lead you to this product? And you would answer, that is definitely only the E starting material that could give you this product right here with this exact stereochemistry. Okay, so the point of this, I guess what has turned into like a 20-minute exercise is basically the stereochemistry of our double bond will impact the ultimate stereochemistry of our products. That is, I guess, the key point there. All right, that's a pretty good little diversion. Let's see. I noticed that we've been doing a lot of these examples with cyclic examples, and so I wanted to now throw in plenty of acyclic examples so we could see what's going on there. All right, so let's just jump right back into reaction. So reaction 8. All right, so the name of this reaction, this is a pretty cool one. So the name of this reaction is ozonolysis, which is exactly what it sounds like. We're going to hit our molecule with O3. We're going to hit it with ozone. All right. And so every good synthetic lab, and this is the honest truth, this reaction does get used a ton in synthetic chemistry. So every good synthetic lab has an ozonator, which basically is a big box that's going to produce ozone, and ozone's pretty toxic, so you have to be careful with it. But you're going to have a tube coming out of your ozonator, and so your ozonator is going to create ozone that you can pump into your reaction flask and ultimately treat your double bond with plenty of ozone. Okay. So this is actually a pretty cool one, and this one is fairly unique. All right. So what do we have happen? We're going to start out with a starting material. We'll just use this very symmetrical alkene. All right. So this is what 2,3 butene. Yeah. All right. 2,3 dimethyl butene, I should say. All right. So we're going to hit this thing in our first step with O3. All right, that's fine. So then ultimately, what we'll have to do is work up. And so this is a case where we're actually going to have two options for a workup. And so each option is going to lead to a slightly different material, but we're going to worry about the nuances of that in a few minutes. So we'll just say that there are two possibilities. We can see an oxidative or a reductive workup. All right, so two possibilities for the workup, yeah. And so the product, let's label this carbon number 1, and let's label this number 2. And so basically, when it comes to the ozonolysis reaction, it's all about one word. It is all about cleavage. Okay, so what we're going to do is we're going to show this blue squiggly line across our alkene here. And so what we're doing is we're literally going to cleave the two halves of this molecule, right? So we're going to end up with a top half, and we're going to end up with a bottom half. And so how many products will we end up with? Two, right? We can end up with 2 products because we really are going to split this thing in half. So we're going to have the top half come out as a product, and we're going to have the bottom half come out as a product. So what do these things look like? Let's see. All right, so we keep the structure of our top side. And interestingly enough, we're going to keep our double bond, but instead of that carbon number 1 being double bonded to a carbon, it's now going to be double bonded to an oxygen.
Is the other one bonded to an O2?
What's that?
I was going to say, is the other one bonded to an O2?
So the other one is going to be double bonded to, wait for it. Are you waiting? Just another oxygen.
Hey!
All right, so basically, what was that?
What happens to the third oxygen?
Weird things. Weird things that are way beyond the scope of this class. All right. Yeah, so essentially what we do is we cleave our double bond, and so we end up with 2 products here. And so have you ever seen any big molecules that have what we call a carbonyl group in them?
Yeah.
That's C double bonded to an O? That's everywhere. And so what it is this gives us a nice easy way that we convert our alkene to this double bond here that I'm showing. Okay, so let's talk about the workups first. Okay, so as I was saying, we've got 2 possible workups for an ozonolysis reaction. So 2 possible workups. And so we'll just show what can happen. All right, so we'll start with a starting material that looks like so in our top case, we'll treat it with O3, and we'll do what we call a reductive workup. And so what we're going to react with is dimethyl sulfide. So it's a relatively simple molecule. So this is our reductive workup. And so the 2 products that we get out, what we're going to have is, again, it's all about cleavage. So we're going to cleave this thing. So you can pretty much just redraw the molecule as is. Add a double bond, so we've got, and actually let's call this side 1, let's call this side 2, and so we'll do the same thing over here. So this is side 1, and we can also have side 2, and so you can see that basically when we do a reductive workup, nothing's going to change. Everything's going to stay exactly the same. So side 2 will end up looking like this right here. All right, so that was to be expected basically based off of what we've seen thus far. So for a reductive workup, nothing changes. However, we're going to see a little bit of difference whenever we do an oxidative workup. Okay, so how do we do that? So we still hit it with O3. But when we do our oxidative workup, what we're going to use is an oxidant, like hydrogen peroxide. Okay, and so this is going to be our oxidative workup. And so what's going to happen is that when we draw our side 1, what we will see is that anytime we have a hydrogen connected to one of the carbons that is being cleaved, that's going to turn into an OH. And so other than that, everything's going to stay the same. It's just whenever we have a hydrogen connected to one of the carbons being cleaved, that gets converted to an OH. And so we end up with two different possibilities. What you'll learn, I think, in Orgo 2 is that this is a type of carbonyl called an aldehyde. This is a type of carbonyl called a carboxylic acid, right? And so what it is we now have two different functional groups that we can ultimately make based on which workup we choose. And so on the right side, the same thing will happen. Any H's connected to our carbon being cleaved will be converted to an OH. Do we have any here? Two. Yeah, absolutely. And so what we would end up with would be this product. And in reality, this one specifically is pretty unstable, but we don't know that. So we'll just say we end up with these two products. And so whenever we do an oxidative workup, we'll say that H's connected to the C being cleaved change to OH's. And that's pretty much the difference. All right, so we're cleaving, and then we want to pay attention if we're doing a reductive workup or an oxidative workup. Mechanistically, how does this thing work? All right, so it's a little tricky. So we'll use this guy. So what we're going to do is show an ozone molecule. And so ozone is kind of a funky molecule in that you can't draw a resonance structure that is neutral. So basically ozone is going to resonate between there being a negative charge on the top oxygen or there being a negative charge on the bottom oxygen, right? And so we can get to that by taking a lone pair here, forming a double bond. In doing so, this oxygen would violate the octet rule and so kick this pi bond down onto a lone pair. So we have a couple of resonance structures. Let's actually show that. This is a fairly canonical example of resonance here in organic chemistry. So the other resonance structure looks like this, but no matter what we do, we can't neutralize these charges because that would violate the octet rule in doing so. So we'll never have two pi bonds, two full pi bonds in this reaction, or in this molecule. Okay, so how does this thing go? Where do you think we start our first arrow? Yeah, you got it. So what we'll do is we'll draw that to there. So this is going to look pretty similar to the osmium tetroxide. And so we do that, and ultimately our third arrow comes from a lone pair on that other oxygen itself. So the structure that we end up with, since it's a concerted mechanism, it must be syn. So we'll have our new CO bonds on the same side. And so we end up with this neutral structure that looks like that. And so this is a stable intermediate, and well, this is relatively, there's a couple of intermediates. This is one of them. So I was making my notes on the plane on Sunday evening, so I was working on this. And so my wife looks over, she usually doesn't care at all about chemistry stuff. And she was like, what is that thing? And so I told her what it is, and I told her it was a stable intermediate. And she was like, well, what purpose does it have? And I told her that it doesn't have nothing. Molecules don't always have a purpose, right? Why do they exist? It's because they're stable. Like, they don't all serve a purpose, right? Nitrogen gas, there's a ton of it in the air. It doesn't serve too much of a purpose. It's just there because it's stable. And so I told her, well, is this because it's stable, not because it serves a purpose? And she just looked at me coldly and said, like our marriage. Point on. I know. That actually happened. All right, so at this point, we're just going to say that stuff happens. There's a lot of weird stuff that happens. So in this case, what we'll do is we'll show a reductive workup. And so this is interesting because now we see our double bond is part of a ring, right? And so how many products are we going to end up with? If we cleave here, our two products are still connected to each other through the other part of the ring, right? So in this case, we're going to only end up with one product, and so this is a cool example of when you cleave, or when you use ozonolysis on a cycloalkene, it basically opens the ring up. And so what we end up with on the right side of the product would be this right here. All right, so to prove that, we've got carbon 1, 2, 3, 4, 5, 6, and so we can just trace that right back around. And so in both cases, you can see that carbon 2, what we've done is we've cleaved off that double bond, and so now it's connected to an oxygen through a double bond, so that's what we've got there. And then carbon number 6, it was involved in a double bond to a carbon, we've cleaved that, and we've basically now double bonded it to an oxygen. Yeah? What's that? Yeah, that third oxygen, it goes and does stuff. We don't do that.
Are you always going to do the oxidative workup with H2O2?
There are other ones, but we'll focus on H2O2. Yeah. But hey, we still have another question.
Why do you now have 6 carbons?
So we had 6 to begin with, right? We had a 5-membered ring, but then we also had a methyl group there. Yeah. Okay, workshop this evening, 4 to 6. Yeah, if not, I'll send an email.
Dr. Walt? Sorry, I have a question. Like here, like
I would only do the
the
couple of last
circuit, right? It goes down, and then you change the bond.
Right, because all right. So what it is
But here, like, why did you change this fashion?
so here we're doing a bond rotation, right? So we're just keeping this in place. Our chlorine we're gonna flip 180 degrees to be on top, and so our hydrogen, if it's coming out towards us, up in the direction of the back of this, 180 degrees from that is going back into the plane, right? So up here, what I'm showing is basically now a tack. So in this picture, we added our osmium tetroxide from the top face, which pushed this down. And so that's why we have our methyl on the dash here, methyl ester. In the other example, we added our OHs from the bottom, which has pushed them up to the top.
So it's not.
Yeah, it's not rotated. It's actually, it would be 2 different products if it weren't meso.
Okay, thank you.
Is this the only starting material? Like there wouldn't be a Z?
So the Z starting material would give us a diastereomer of that, basically. It would
Okay.
give us a different product.
Okay.
Yeah.
Of this, right?
Yeah,
okay,
it would. You'd
that
have the
makes
same
sense.
connectivity,
Okay.
but you'd have different stereochemistry.
Thank you.
Yeah.
We're kind of confused with how meso, like how those are the same molecule and like the wedges and dashes are different if you were to flip it. And
So when I say flip it, I mean literally. All right. So let's make this. This is our carbon-carbon bond. We're just gonna change the ends like that. And so just like if my hand is like this and my thumb is on a wedge coming towards you, if I flip this 180 degrees, my thumb is still on a wedge, right? And so we're doing the same thing here. So we've got our hydrogen on a wedge. We're going to flip it over 180 degrees, and it's still going to end up on a wedge once it transfers over. So here's our, basically, if my hand is this carbon with my hydrogen on a wedge coming
Well, if your
towards you, and I flip this
hydroxyls
thing
aren't
like
lined
this,
up, what I would
now
do
on
is
the other side,
you just
it's this
rotate that
carbon,
hydroxyl,
but it's
then
still
you have
gonna
the
be
R
on
and
a
the
wedge,
S
right? It's still
on
coming out.
opposite wedges
But
and
this one's
dashes,
upside
and then you
down
can just think
compared
about
to
it as like
Yeah,
folding it
exactly.
over.
That's
how I like
that's
it.
why they're the same molecule. It's just one of them's upside down. So we flipped it. We basically it's
just like I was
they're
like
flipped
trying to
180
rotate it.
from each other. But what we ultimately find is they're the same
Seems like
molecule.
you can,
If you don't
like-
believe me,
I'm
just
really
try to
good.
take
Rotating,
basically
yes.
try to find the
To be honest,
enantiomer
I spend
of either of
about
these, and what you're
95%
going
of
to
my
find
time
is it's the
rotating
same
bonds.
molecule. It's meso.
Interesting. Are you
Okay.
overlap?
Yeah.
No, just like I do it all the time. Like all I
I guess
do
that's
is
just
like I
not
write
fair.
out the bonds and I just try to rotate them until they make
Yeah.
sense because they don't make any sense to me
I'm
ever.
just wondering if this is like the correct answer for that.
All right, so I'm showing it anti, and so the methyl and hydrogen will be on the same side. Yeah, that looks good.
And also, I'm just like still confused about like how if I can determine if it's cis or trans.
So cis or trans, you have to have a hydrogen off of each carbon, right? And so in this case, we've got a hydrogen off of this carbon, but not off of this carbon. So we can't use cis or trans, and we would have to use E or C.
Do we need to know how to name structures with like